Hey, our next lesson is on factoring a difference of squares. Now, a difference of squares is a very particular pattern we're going to be studying, and we'll talk about that later. Your prior knowledge pretty much is going to be multiplying polynomials and applying the zero product property. So if you need to review those, look those over, that's great. But in our warm-up right now, you'll notice that this is covering multiplying polynomials. So here's what I want you to do. Pause right now, multiply these out. Now what I want you to do though is look out for patterns, as I said, okay? Maybe you do A and B and try to think, can I get away with not doing any work and just predicting the answers to like C and D? Try to do that and then we'll look at it ourselves, okay? So go ahead and pause right now. All right, so hopefully you notice something happening with each one of these. Now if you look at each one of these very carefully, you'll notice it's always the sum times the difference of two identical things. So in this case, it's x and 3. So x plus 3 times x minus 3. And this one, well, the difference is first, but it doesn't really matter which order, right? So we have the sum of x and 8 times the difference of x and 8. And then x and 12. And then here 2x and 5 and 2x minus 5. But there's a common thing happening when you multiply these all out, right? So let's just do the answers. I'm not going to show all the workout for all of these, but maybe for the first one. If we actually distribute this, we get x squared plus 3x, but then you're going to get a minus 3x, and then you're going to have minus 9, because 3 times negative 3 gives me that minus 9. And you'll notice this plus 3x minus 3x, those cancel out. So all we have left is x squared minus 9. Okay? And in this one here, you'll notice that we have x squared minus 64 once you simplify it all out. So look real carefully at how we got that. And the next one, x squared minus 144. And then this one is not just going to be x squared. You're going to have a 4x squared, right? Because we got the 2x times 2x. And then minus 25. So hopefully you notice that pattern there. So now we can officially state this as an actual rule. Now this rule is actually it's got a common name. It's called the difference of squares pattern. So that's something you should tuck away into your pocket and make sure that you remember that, okay? You got it? So this rule says for any numbers a and b, if you take their sum and multiply it by their difference, that's always going to give you the same result as if you did this calculation instead. If you square the first number and subtract the square of the second number. That makes sense? Okay? So just as a quick thing, like we actually use numbers. Think of two numbers. Let's say 3 and 8. If I do 3 plus 8 times 3 minus 8, that's going to be the same as 3 squared minus 8 squared. That's all we're saying. Any two numbers you can pull out of your head, if you actually did this calculation separately, this one and then this one, you're always going to get the same thing. They'll be equal. So this would be 11, right? And 3 minus 8 is negative 5. And that gives me negative 55, right? And then watch this. 3 squared is 9 minus 64. And that's actually also equal to negative 55. So there's just a very plain example for remembering what an identity is. Remember, no matter what numbers you plug in here for A and B, this calculation on the left is always going to be equal to this calculation. Okay? As opposed to just a random equation we're saying solve this, maybe there's only certain numbers that make it true. This one is just always going to be true no matter what numbers you choose. Okay? So most of the time you and I are going to be working with variables involved with this pattern though. But since variables represent numbers, that rule still works. Okay? And we'll do plenty of examples today to go with this. We're going to actually prove this rule. We kind of already have, I think, in the past, but we can show it again today. If we take algebraically, if we take a plus b and a minus b, and we just do our distribution, right? So we'll take this a and distribute it into there, and then this b and distribute it into there, right? Then we just finish simplifying and we notice this has a minus ab plus ab, and then in the end we just have our a squared minus b squared in the end. Pretty simple rule to prove, but it's a very helpful rule though. Or you could use an expansion box, and either way in the end you're going to see these two like terms still end up canceling out, and we get the same rule. I think there's some very beautiful visual ways to prove this as well, and that's what we're going to kind of look at next. I have some cutouts actually that we're going to look at, and we're going to look at some things you've seen in the past you're going to recognize. So you might want to think back to an activity that we did in the very beginning of the year called hollow squares. You might also want to think to that fountain problem that we did recently, and we're going to look at, in fact we still have our cutout from that, and we're going to look at some really neat, interesting visual ways for this. So like many proofs that exist in math, there is a really beautiful visual way to look at it, and it's actually going to revolve around area. So we're thinking about finding the area of a square removed from a square. And if you think about the words difference of squares, aka a squared minus b squared, right? This is the difference of two squares. And when we square something, we can always relate that to the area of a square. So in our case, here's a big square, and we're removing a little one from it. And this should look very familiar to you, because if this has side length a, the big square, and then the little one has side length b, right? Then you can think of this as a squared, the area of the large square, and when I take away or remove the area of the little square, its area is b squared, then we get a squared minus b squared. And what we're going to look at now is two different ways to calculate the area of this shape actually, without just directly subtracting the bigger area minus the smaller one. And you will see that we will notice that this expression is actually equivalent to a plus b times a minus b from breaking this apart into pieces. So remember, another way to find areas is we can always cut the main shape and then rearrange it, because we know the area doesn't change even if we rearrange it. So what I did here is I cut from this corner all the way up to that corner, and we can pull that apart, right? And this is the same identical original shape, but you'll notice I have two equal pieces here, although they're flipped from each other, they're reflected. And I can move either of these around as much as I want, and still this and this together is going to have the same total area as that. So watch what we're going to do here. It's going to turn out to be pretty neat. I'm going to move this a little bit down here. Now I think you guys all agree with me that this still has side length A and this still has side length B. We haven't changed the shape here, right? Because we're trying to show that the way we did it here and the way we do it here, even if they're different, the areas must be equal. Well, what is this length right here? The easiest way to think of it is just actually kind of like we did this, but not in 2 dimensions with area. We can think of it as 1 dimension. So the whole thing has length A, right? But we've taken away this much of it, but that's B. So actually what's remaining is A minus B, and that's how long this short section is. So watch this crazy thing I'm going to do. I'm going to move this, but I'm going to flip it across here, and I'm going to rematch it up. And you can see, because that length still is the same, that diagonal, I've been able to rearrange this into a rectangle. Well, rectangle area is really easy to find, because we just take our length times our width. So the area of this one is a squared minus b squared, but if we think of it in a different way, remember the short one is b and the long one is a. So that's b, this is a, and this is still a minus b like we had down there. But in the end, what is the area of this rectangle? Well, it's the length times the width. So the area here is a plus b times a minus b. And since this area and that area must be the same, we can say a squared minus b squared is the same as a plus b times a minus b. Super cool, huh? And there's another way to break this down and still get this result with a different cut. Instead, what I did was I just cut it right here. And this is still A, and this is still B, but notice when I remove this, I had A and I took B away. So this has A minus B as its width. Maybe you recognize that it's the same as that. And what I'm going to do is I'm not going to ignore this piece. I'm just going to rearrange like I did before. And you'll notice here, don't forget this was b. This shows length times width is a plus b times a minus b. And again, remember the total area, even though I've cut and rearranged, is still going to have to be equal to the original thing. And so we can see from this visual proof that's really cool that a squared minus b squared and a plus b times a minus b, these are all the same as each other. Okay? Now there's one more proof or description I'm going to give related to our talk of the multiplication table we did in the last lesson. Okay, so for our last proof or way of showing this difference of squares property, we're going to actually revisit the multiplication table. And if you want, you can actually get that out. I gave you guys a blank copy of it, and you could fill this in so you don't have to draw it all out. But we're going to look at this diagonal here. You remember before we put a perfect square in the center, and we looked what happens if I go up or down, left or right, or on this diagonal, or on this diagonal. And we're going to stick to focusing on this one. Now if you remember, this diagonal is what contains all the perfect squares. So 1 squared, 2 squared, 3 squared, 4 squared, blah, blah, blah. And we'll just call this a squared. So it could be 6, so 6 squared, which is 36, or whatever, but we're going to leave it as a. Now I want you guys to remember something. This came from a times a, right? So 1, 2, 3, 4, whatever this is, okay? And a times a makes a squared. Well again, what goes above a? What's the next number up? A plus 1. And same here, this one here is a plus 1, and then this is a plus 2, and then of course we could continue on, and this can be a plus 2, and then of course, etc. Right? And let's think back. What happened as we went on this diagonal in our last lesson? What happened when I went out once? This just subtracted by 1. So that would be just a squared minus 1, and this would be a squared minus 1. Well, what happened when I went out 2? A squared minus, it actually from here to get there, we subtracted 4, if you remember. So it's tempting to think this is 1, 2, 3, etc. But actually just go back to the multiplication table and look at the patterns, and you'll see that this one goes down by 1, but then this one goes down by 4. And same with this one. And then the next one goes down by 9. So this is also a squared minus 9, etc. Okay, and that's if this one is a plus 3 and a plus 3. So here's the cool thing, and it just relates to what we did. Watch. How did we get to this space? Well, if you were to remember going down here, if I go down 1, this is a minus 1, and then I guess I should go down a little more, right? And that matches with this, and then if I go down, that's a minus 2. So watch what happens here. This part of the multiplication table is the product of this guy and this guy. Well, a plus 2 times a minus 2 we've actually, if we just apply that pattern, if we take this thing minus that, this squared minus that squared, we get a squared minus 2 squared, which is a squared minus 4. And that's exactly what we get if we multiply it out. So we can actually see that this diagonal helps us notice as well. Because from the center, if I go up 2 and then down 2, I'm at a squared minus 4. And that's the product of a plus 2 times a minus 2. And if we actually went up b and down b, it would actually show, and let's just use that here. Let's just say this is b up, so this is a plus b, and same with this one here. We've gone up b. This is going to be a plus b, and here would be a minus b. So a plus b times a minus b gives me a squared minus b squared. because you'll notice 4 is 2 squared, 1 is 1 squared, and so this fits the same thing. So this is just another interesting pattern. Try to understand these ways that we've proven this just because it's a good thinking exercise. But the main thing you need to know is the actual pattern itself, and then we're going to jump into using it.